right. Is this thing on? Oh yeah, it's definitely on. All right, thanks everyone, and for staying almost right to the very end. I believe there's one more after me. I don't know who did the scheduling and the deciding who goes after who, but this is perfect. I get to skip over a bunch of my early slides after that last speaker, so amazing. I'm going to be talking about the dark forest, private CRDTs as a global database, or how to power a new internet. My name is Brooklyn Zelenka. You find me anywhere on the internet as Xpeed, and I'm the co-founder and CTO of a company called Vision Codes. And we're working on a whole bunch of protocols, including this whole list here, UCAN, autocodec, dialog, and what I'm mostly going to be talking about today is the web native file system, which does a bunch of the things that the last speaker was talking about at the beginning of the talk. So the situation, where we're at today. Services in 2022 look a little bit like this. We have a couple users, Alice, Bob, and Carol, and they want to log into some music service. So they all go and they create accounts, and of course they do this through some auth service because we don't want to have to deal with all of the extra password resets and all of these things, right? So they log in with maybe a Google account or Twitter login or a GitHub account, something like that, and then that mediates the access into this music app. There's a separate app, and Bob now gets to reuse this same login and store photos, albums, and if we're really lucky, the photo service and the music service talk to each other. And Bob can now use photos from his vacation as album covers or playlist covers in the music service. But this is only, really if we cross our fingers and hope that they've gone and done this extra work. And finally, social media, maybe Bob and Carol are on some site and they want to talk to each other. And this is yet again, some data is separate from their music, which is separate from their photos. And so if they want to share a photo from the Bob's Photo app, often you have to download the photo and re-upload it, right? The other problem that seems to be happening increasingly is around ownership and governance of these different services. So we'll take just a completely random billionaire like Elon Musk were to, I don't know, try to buy a social media company. And who knows what they're going to do with that, right? And maybe you don't like their policies, or maybe they shut the service down, and now what happens to your data? Well, that's not so great. It either goes away, maybe if you're lucky they provide you with some sort of an export function. Fundamentally, you don't own your own data, right? Problem 2, there's too much in between us, developers, and the end user. There's a lot to learn, maintain, hire for, and just to keep a simple app going, you have to learn browser APIs, GraphQL, server, become a database expert, and DevOps, because obviously Kubernetes must be really simple, just as doing data engineering must be really easy, right? So if software is going to eat the world, we need to somehow find a way of making this huge towering stack smaller. And third is in the same way that in the early 2000s, we thought it was OK to put credit card numbers in our database until those would get hacked and a bunch of credit card numbers would get leaked, and you would never do that now. I think as a society, we're realizing that having personal identifiable information in a database is a bad idea. And in fact, we're getting regulation, famously GDPR, but also regulation all around the world, saying that you have to actually be really careful with people's data now. So the best way to handle this is just to not hold anybody's data at all. So what if, instead of building apps the same way we've been doing for the past 30 years, which is fundamentally extensions to the LAMP-style architecture, we inverted the model and said users owned their own data. We could load an application into Bob's context, and just like how on your phone it asks you, you open up a photo app and it says, do you want to use the photo album from the Photos app? And you go, yeah, absolutely, I would love to do that. We can do this across multiple stores. So social media then could pull in data from, in this case, mostly Carol and a little bit of Bob. And music, maybe we want to provide it data from all these different places. I haven't talked about an auth service here at all because you don't need one. The user's in control of their data, and they're providing data to services. Open protocols have been a major, major driver of essentially everything that we do. This conference exists because of TCP/IP, HTTP, things like that. And that's open protocols at the networking layer, and there's a whole bunch more. But what we're starting to see in the past couple of years is opening up of protocols for other things, like auth, so you can do permissions without pre-negotiating. Data, so you can have ubiquitous sort of dumb storage that the application knows more what to do with, but that the actual storage portion is fully commoditized, and you can just say, yeah, I'll store this locally myself, or I can hand this off to somebody else and let them store it. And compute, so that local functions can run the same as they run remotely. So we don't need to set up a particular account on, say, AWS Lambda. We can run it locally, the same as we run it on an edge worker, as we run on in the cloud. And there's tons of stuff to talk about in there. This rest of this talk is really going to just talk about the data layer. So I'm going to cover 3 broad techniques. Things for global primary keys, portable private data, and Byzantine fault-tolerant concurrency, which is a bit of a mouthful. And the 3 here will be content addressing, crypt trees, or an extension to it called dark forest, and hash-linked CRDTs. So let's start with content addressing. These are truly global links. One of my all-time favorite quotes is from Nancy Lynch, who says that the limitation of local knowledge is a fundamental fact about distributed systems, and that this is, ultimately the real limitation of the internet, right? Even if I've made a request, 100 milliseconds ago, who knows what's on that other machine now, right? The speed of light is finite, and that limits causality and the flow of information. So in order to make these problems even tractable, we need to find ways of finding universal things so that we can even talk about data at all, but so that if I have data locally and you have data remotely, that we can talk about it in a consistent way. Traditionally, we've used location addressing. So this is, you have a IP address and some path. And if I ask for that same IP address, the same path twice, I might get different content, right? First time it's a photo, second time it's a same photo with a funny mustache on it. And we're not asking for the content in this case. We're asking for, give me whatever happens to live there. It's like going into a library and asking not for, I want this book. It's like, well, I want whatever's on the 3rd floor, this many shelves in, this far back on, the 3rd book in, and whatever, oh, that happens to be War and Peace, right? It would be much easier to be able to go to the front counter and say, where can I find War and Peace? DNS makes this a little bit more human readable, but it doesn't actually solve that problem, right? And so we're seeing, actually, content addressing has been around for a little bit now, but we're now seeing this in really networked cases where to identify the content, we just take its hash. And if I take a SHA-2 of some content, or you do it, it doesn't matter. We get the same hash back. And so that's kind of like saying, give me this book, and I can go to a bookstore, or I can go to a library anywhere in the world, and we can reference that exact same thing. This lets us have global pointers that we can all agree on for the same data. So here's some chunk of data. It has links inside of it. And one of the links is called company. And that'll point out to some other data that also has a hash. Right? So this is just JSON, just regular normal JSON. But instead of using keys inside of a database that I happen to have generated sequentially locally, we're just using its hash. And the other advantage of this is that because hashes can't change, and referencing these hashes inside of each other, once we have the first one, we can use a nice human readable path from that point onwards. And so we don't have to deal with hashes most of the time. It's just at this top layer. And you can put a naming scheme on top of it like DNS as well. This adds a fundamental new thing to the internet, right? We've had links on the internet from the very beginning. It's the entire point, right? Here's 2 separate data stores. And I can have soft links, essentially symlinks, which are literally URLs, right? And if you think about this from how you've been working on your computer, if only you had symlinks, symlinks can break. They can lead to nothing. They can change what kind of data is behind them. But hard links, these new content IDs or CIDs, stay in place. They never change, right? And so this gives us a fundamental new building block for linking data around. This doesn't have to be too scary. Here's a really simple content address store that whipped up in a couple of minutes. And basically, it is a map of hashes to, in this case, array buffers, just to keep it simple. And when we go to put something into the store, I don't have to give it the key to say key value, because I don't have a choice of key, right? I'm going to hash it. We're going to take the base 64 of that hash, and then store it as that hash, the value that I gave it. And then return to the user the key that has this special relationship to the value that then, if I need that data back, I can just ask for that key and return me that value. And if I do this, or if I do this over the network, it doesn't matter. It's going to look the same. So this has given us a consistent way to reference data with hard links, which is new for the web. We can also self-verify the data. So if I receive a file back, I can hash it and check, oh yeah, that's actually the thing I asked for, because the hash matches. And the names, and this will become more important later, the names leak no additional information about what's inside of it. So I can give you a list of things and say, I guarantee you that I have all of these things, but you don't necessarily need to know what's inside of those. So let's talk about the actual data for distributed storage. Inside of a file system, it's pretty simple. You have files, shocking, which have the raw data, the actual payload, and some metadata. So if you're in the terminal and you ls, you'll get a whole bunch of these will pop up. And metadata can be things like last time it was updated, or who did the write, things like that. And then, of course, we have directories, right? And directories can contain other directories or files. We've all seen this for decades at this point, right? The difference here is we're saying it doesn't have to only live on your disk. These can now be networked and live anywhere, and even different parts of the file system. One part can live here, one part can live there. It doesn't matter, because we now have these new networked links. The one thing, in addition, that we've had to add, for reasons that will become apparent later in the talk, is persistence and versioning. This is sometimes called a temporal data structure. So here I have photos that has two subdirectories, vacation and avatars, and then respectively beach and caricature. And over time, I, of course, want to change this data, but I have hashes. Hashes can't change, right? So here's I want to add this headshot inside, which means I have to change the parent directory, avatars, which is now @1. And we point back at everything that hasn't changed. So we also include this caricature. And we go up one more level and say, well, I guess photos has to change because its avatars directory has changed. And we're going to share the structure from vacation as well. So we've just added a couple links, and we get a new version. But we also get all of the history and all of the events behind that. If anybody's ever used Time Machine on a Mac, this is literally what they do. It's almost exactly the same. They're literally using hard links, but just Unix hard links instead of networked ones. This also looks pretty simple under the hood. So this is the part that a framework would handle. And it says this is a file, not a directory. It has these in its history, right? So we have a couple different these links and the event that changed it. We have some metadata, last time it was updated, and who did the updates, and then the actual content itself. In this case, because it's JSON base 64, but if you used something like CBOR, you just have the raw bytes. And this is supposed to be about encrypted data, so that's just public data. We need to be able to move data around anywhere. So again, completely locally, post it to a backend service, even services that maybe I don't completely trust. So I need to be able to encrypt this data and sign things about this data. And the good news is that the tools for cryptography are actually getting pretty good these days. So the WebCrypto API, and specifically SubtleCrypto, is now available in essentially literally everywhere for the past several years. And this is especially important, yes, you can do the encryption part, but especially for doing key management. So if you're in a browser and you have one of these keys, the problem is that a malicious user could show up, or a web extension, or a bad application, and steal your key and run off with it, right? Because it's no longer sitting behind an access control layer. It is the access control. But the WebCrypto API sits between them and the key and says, all that you can do is generate documents, send them to me to sign, and I'll send you back the signature. And that's it. You never get direct access to the key at all. So it doesn't solve all of the security problems, but it does a pretty good job putting a dent into key management in the browser. Showing that you actually own some data can be done, again, with a bit of hashes and some signatures. So this is the same hash-linked data that we were talking about right at the beginning. Those are all the hashes next to it. And we can put in some well-known path information, not personal information about you, but some signature that says, hey, I own this thing. And that will change that top hash. And if somebody else comes along and copies my data store and says, actually, I own this, that will change this top hash as well. So we now have a way of saying, proving that I'm the one and only owner of this thing, and somebody else has copied the data, and they're making a bunch of other changes to it. That's a different copy. And so now we have uniqueness on the data. Actually being able to read encrypted data, there's always starting from the UX and the access control patterns. So if you are using Google Drive or Dropbox or something like that, you want to be able to give somebody the ability to read a directory and all of its children, all of its contents, or maybe just a single file, or something in between, or a bunch of files, or across multiple different data stores, right? We shouldn't care where the data is coming from, just that I'm giving you access to these particular things, or that people in a group are handing out access to certain parts. And then I can look it up in a shared directory and say, well, which parts of these am I able to see? And I can have links and keys to them. So how does that actually work when we don't have a server sitting in between checking, are you who you say you are? Yes, great. Are you on the list? And then I can send this to you. This has to work offline, everywhere, regardless of where it's stored. So we start with a totally flat data structure. So it's any kind of a set of just encrypted random-looking blobs from the outside. And I give you a key and a pointer to one of those. And that will decrypt this first directory in this case. And inside of that has pointers down to either more directories or more files and their keys. And because I have the pointers, I know which other ones of these to go and look for. So over time, we can walk through this tree and rediscover the structure. So going from this totally flat thing to the structure of the file system that I'm actually reading from. And because I have this top key, and that contains all of its children, and all those children contain all of their children, you can recover, by only giving a single key, all of these other keys inside. We found the most effective way of storing this is using something called a hash array map trie, or HAMT. But really, any kind of flat data structure would work really, really well. The important part here is that it doesn't leak the structure of the file system, right? It's completely flat. And once you get that first key, that means that you're authorized to understand more of the, this metadata, more of the structure. Then you can start seeing the relationships and the hierarchy between these links. Finally, we want to be able to not just read and prove that we have access to this thing, but also make writes concurrently. Right? So I want to be able to write into it while I'm offline, and somebody else should also be able to collaborate with me. Or we should be able to do a collaborative document, for example, like a Google Docs. The fundamental problem, always, is network partitions. So somebody goes offline, or the Wi-Fi drops or something, and the speed of light. And the speed of light is, there's literally no way to fix that, right? So one way of thinking of this is as a light cone, where you're in the middle, and if you create some information, that can only go so far in a certain amount of time. So you can almost think of it as rippling out from a certain point and gaining more space. And so we can think of it a little bit like this, right? And if you have collaborators that are like far other side of the planet, not only will it take time for that to arrive, but based on where people are located, it'll arrive in a different order. And that seems like a really tricky problem, right? And one of the other things that we found is when you have things like encryption, that behaves the same as extreme latency until you have the key. It's like the message has just arrived, or a network partition. So all of these end up being the same problem in the end. So how do we even make this problem tractable at all, right? How do we handle ordering when we don't have a single central server that says this happened, then this happened, then this happened, because it's the single source of truth? How do you have ordering when you have no source of truth? Well, here's Alice, Bob, and Carol again as 3 colors, and they're going to send messages to each other saying, these are the colors I know about, and we're going to do this by mixing color. Time goes to the right, so sending some messages, and they're off, and there's lots of stuff happening, and it's, very complex, and this is just for three actors. At the end, we've all ended up in the same state. We're all in brown. Here's yellow has arrived at blue and changed it green. It said, well, I'm not really sure if you know about all of my stuff, so it sends a message back. Green already has the yellow component, so it doesn't have to, or sorry, yellow already has the yellow component of the green. So it just says, I'll just adopt green completely. And this last one here took a really long time, even though it was sent right at the beginning, to get to the end. But it already had it from the green message down there, and nothing had to change, right? And so it doesn't matter how many times we send these messages, it's actually completely fine, and we'll always get back to the same state. Entropy is really, really difficult in these systems, and we can essentially make it simpler by using 3 properties and this little technique called math. It's sometimes a little bit helpful. So the 3 properties are commutativity, which says that if you have order doesn't matter, so if you do blue or red first, you'll still get back to purple. Associativity, which says if you have 3 or more things, the way that you bracket them doesn't matter. So here I do those 2, so I can do yellow, then blue, and then red, or vice versa. And the intermediate state here is different, right? I've got green or purple, but at the end, when all 3 of them are together, we get the same result. And finally, idempotence, which says I can do something once or many times, and I'll get the same result. So it's like having something that's empty, and you're going to fill it, but you can only fill it once. And so if you try to fill it again, well, you're still in the same state. You still have this same thing. So how does this apply to doing async distributed local first file systems? Well, we have that persistent data structure that we talked about way at the beginning, right? And it has history. So we can have an entire, have an entire history chain back here. So this B node came after A, and it updated it. D didn't know about B yet, and so it said, actually, I know about C and A, so I'm going to make a new update to D, and we can keep moving up and up and up. And it's a little bit like automatic git merge at the file level. We also have ways of doing this in subfiles, but we're trying to keep it down to 25 minutes. So you can do that automatic. You can ask the user, hey, did I get the right one? And if you got the wrong one, they can look back in time and say, actually, I wanted this version, or I don't like how you reconciled those. I'm going to write a new version instead of that. So it's all non-destructive. It also means that you can do this between multiple different file systems. They don't even have to be forked off of the same one. They can be completely separate, and you can have 2 of them and compare them and just merge them together. So maybe you have 2 photo galleries that you want to merge together. That's entirely doable in this model, automatically with just baked in. The other thing to note is you can have different histories end up in the same state. And so you can do things like compress history over time. So we're going to have people talking about their favorite animals, a dog, a cat, and an octopus. No judgment. Maybe the dog lover learns that there's a cat lover, and the cat lover learns that there's somebody who likes the octopus, and then they all learn about each other. But at the same time, there could have been somebody who doesn't know about most of the other ones, and we can have this split off and getting to this over time as we learn about things and as latency happens and as we get more encryption keys, we learn about the complete state. That's not the interesting part. The interesting bit is we didn't actually need these intermediate ones at all. So if we had either of those histories, it doesn't matter, right? We can still end up in the same state, and we can compress history and save some space. So I realize that it's like a crash course in CRDTs, which are famously just adjoint semi-lattice over causal relations. But there's only so many of these. There's about 15 or 20 CRDTs that we know of today. They're actually really simple to get started with. The hard part is making them behave the way users expect. But again, we can bake these directly into applications and directly into something like a file system. So to wrap up, again, this is a 25-minute talk. They're pretty fast. We've only really talked about this section of this graph. There's quite a bit more in here to make this stuff really usable for end users and for developers who don't want to have to worry about how am I going to actually merge data together, right? And fundamentally, we've tried to make the web an open platform several times, and repeatedly, I think people in general, humans, tend towards centralization over time. But if we can build some really good open interoperable tools, we can have an open platform this time and really mean it. So, thank you.